Hari Om girls. In the elective course Information Security, we are currently discussing Module 2, in which we are talking about the polyalphabetic ciphers of substitution cipher. In our previous video, we have covered auto key cipher, playfair cipher, beginner cipher, and hill cipher. And some of you have texted me that hill cipher need to be repeated again. So in this video, I will be covering hill cipher, one-time pad, rotor cipher, and Enigma Machine. Getting into the hill cipher, this is another interesting example of polyalphabetic cipher. And this is a polyalphabetic substitution cipher which is based on linear algebra, and it is invented by Lester Hill in 1929. Unlike the other polyalphabetic ciphers which we have already discussed, here the plain text is divided into equal size blocks, and these blocks are encrypted one at a time in such a way that each character in the block contributes to the encryption of other characters in the block. I repeat, the blocks are encrypted one at a time in such a way that each character in the block contributes to the encryption of other characters in the block. Now this cipher actually belongs to the block cipher category. We will be discussing the stream cipher and block cipher in the upcoming videos. So just we have to understand hill cipher is a category of block cipher. Let us see an example of hill cipher and the encipherment process so that it will make clear what do you mean by the blocks are encrypted one at a time and each character in the block contributes to the encryption of other characters in the block. Now, if you observe this slide, the key in the hill cipher is a square matrix of size m by m, in which m is the size of the block that we prefer. If we call the key matrix as K, each element of the matrix can be denoted as Kij. So Kij is an integer of Z26 set. So this is how the key matrix will be represented. Now let us see how one block of the ciphertext is encrypted. So this is the process that we are going to use for encryption in the hill cipher. Let us assume that the plain text is divided into n number of blocks where m is the size of the block. So that means P1 to PM will be one plain text block which is to be encrypted. So if P1 to PM is one block in the plain text, it will be encrypted to a ciphertext block C1 to CM. I repeat, if P1 to PM is one block in the plain text, then the block will be encrypted to a ciphertext block from C1 to CM. So if so, this is the process done. Each character, observe here, each character depends on all the characters in the block P1 to PM. So C1 will be calculated with P1 to PM block values and the first column of the key matrix. C2 will be calculated with the same block P1 to Pm with the second column of the key matrix. And C3 will be calculated with the same block P1 to Pm but with the third column of the key matrix, and so on. Therefore, we can say each character in the ciphertext block depends on all the characters in the plain text block. And we should also observe here the key matrix in the Hill cipher must have a multiplicative inverse. Only then we can do the decryption process. This is one condition we should understand in the Hill cipher. I repeat, the key matrix in the Hill cipher must have a multiplicative inverse. Only then we can do the decryption process. Now, since key is a square matrix, the encipherment process can be easily done with the matrix multiplication like this. So, if I want to encrypt, the plain text block will also be represented as a matrix and the key matrix will be represented as a square matrix, and this will go for a multiplication process for producing the ciphertext blocks. So, this is going to be the block. Say for example, if the M is the size of the block, M is the size of the block. In this example, 4 is going to be the size of the block. 4 is going to be the size of the block. Therefore, I have the key matrix as 4 by 4 key matrix. Now, since this is the plain text which is having 12 characters, I am going to divide this 12 characters plain text into 3 blocks of each 4 characters. Therefore, I will have a 3 by 4 matrix for the plain text. You can observe the first 4 characters will be in the first block. Then the next 4 characters will be in the second block, I, S, R, E. Then the third block will have A, D, Y. A, D, Y. And since we don't have fourth character, I am going to add a bogus character Z, which will have value 25. So this is how a 3 by 4 matrix is created for the given plain text. Now this 3 by 4 matrix is multiplied with the 4 by 4 key matrix to generate the ciphertext block. So this is the ciphertext block 1, ciphertext block 2, ciphertext block 3. Here this is plain text block 1, plain text block 2, plain text block 3. And if you observe here, this key matrix is having an inverse. So only if I have an inverse, I can do the decryption process. What we do for the decryption process? The ciphertext will be multiplied with the key inverse, which will produce the plain text blocks. So this is what is done in the Hill cipher. So whenever you have a plain text which is to be encrypted using the Hill cipher, the first step is decide what is the block size. Once the block size is decided, create a square matrix of the block size M. Then divide the plain text into n number of blocks, each of M size. If any block is not having the size M, you can add extra bogus character Z or X, whatever it is. Then the plain text blocks will be represented as a matrix and it will be multiplied with the key matrix for producing the ciphertext. So this is a procedure for the Hill cipher. Now in the Hill cipher, obviously we should understand what is the cryptanalysis part of the Hill cipher. Now if you see the cryptanalysis of Hill cipher, the ciphertext only attack is very difficult here because the brute force attack is extremely difficult since the key domain size is going to be 26 power m by m. 26 power m by m, because each entry in the m by m matrix, each entry in the m by m matrix will have 26 values. So obviously the key domain size is going to be very large, so it is very difficult to attack using brute force attack. Now another thing in Hill cipher, it does not preserve the statistics of the plain text. Therefore, frequency analysis is also very difficult in the Hill cipher. Whereas the Hill cipher is exposed to known plain text attack. That is, if the value of m is known to the attacker, and if the attacker has the plain text and ciphertext pairs of at least m blocks, then the attacker can do known plain text attack. How it is possible? If C, which is the ciphertext, is equal to plain text into the key matrix, if C is equal to PK, then K can be found using the ciphertext multiplied with the P inverse. P inverse is nothing but the plain text blocks inverse. So if the attacker has got some plain text and ciphertext pairs, she can try to get the key by using the ciphertext multiplied with the P inverse, which is the plain text inverse. So this is possible if the value of m is known and some plain text and ciphertext pairs are available with the attacker. So this is an example given how the Hill cipher can be attacked using known plain text attack. So if Eve knows that m is equal to 3 and she has got plain text and ciphertext pair blocks like this. So these are the pairs she has got and the m value she guessed as 3. If so, she can try to get the key value by multiplying C with the P inverse. Then she will get the key value which can be used to break any ciphertext encrypted with that particular key. So this is the cryptanalysis part of the Hill cipher. So Hill cipher is safe or secure from the ciphertext only attack, but it is not secure from the known plain text attack. So that's it about the Hill cipher. Now the next cipher is called as one-time pad. Now if you observe, one of the goals of the cryptography is perfect secrecy. We need perfect secrecy. Now a study by Shannon has shown that the perfect secrecy can be achieved if the plain text symbol is encrypted with a key randomly chosen from a key domain. So if the key is randomly chosen from the key domain, then we can make the message very, very secure. So the idea is used in a cipher called one-time pad, which was invented by Burnham. So it is also known as Burnham cipher. Here we take a key to encrypt the plain text where the key length should be the equal length of the plain text. Please make a note of it. If the plain text is having 10 characters, then I am going to have a key which is also having a length of 10 characters. All the 10 characters are randomly chosen from the Z26 set. So if so, it is very difficult for the attacker to find or to guess the key value. But though it is impossible to implement commercially, as the key must be generated and shared each time, this will give you a perfect secrecy. So this simple cipher can become a perfect cipher if the key that is used to encrypt each character is chosen randomly from the key domain. Now here when you see the one-time pad, the one-time pad is secure from ciphertext only attack, and not only that, from other types of attacks are also impossible on one-time pad. And the next cipher is also known as Rotor Cipher. Although one-time pad ciphers are not practical, one step toward more secured encipherment is using the Rotor Cipher. Now this Rotor Cipher is a more secure encipherment process. Now this uses the idea behind monoalphabetic substitution but changes the mapping between the plain text and ciphertext characters for each plain text. I repeat, this Rotor Cipher also uses the idea behind monoalphabetic substitution, but this changes the mapping between the plain text and ciphertext characters for each character. For each character or for each plain text character. Now this diagram shows a simplified example of a Rotor Cipher. So this figure shows only 6 letters, but the actual rotor will have 26 letters. Okay. Now this rotor is the one which is permanently wired, but the connection to encryption and decryption characters is provided by the brushes. So which can be decided by the messengers. Now here we have the initial position, and in this example we have after first rotation, after second rotation is also shown. Now this initial position is the secret key, the initial setting, or you call it as initial position. So this is going to be the secret key which will be shared between Alice and Bob. The initial setting of the rotor will be the secret key which will be shared between Alice and Bob. Now let us see how the encryption is done. So the first character is encrypted using the initial setting, and the second character is encrypted after the first rotation, and the third character is encrypted after the second rotation, and so on. This is how the encryption process will be done. Now suppose, say for example, we want to encrypt the text BEE, then let us see what will be the encrypted data. Now if the rotor is stationary, if it is not rotating at all, if you are not rotating at all, this BEE will be encrypted to BAA. How? So the B is having the ciphertext as A, E is having the ciphertext as, this B is the plain text and these are the ciphertext. So this B is encrypted to capital B and this E is encrypted to capital A. So if the rotor is stationary and it is not rotated, then BAA will be the ciphertext. But if it is being rotated, what we will do? The first character will be encrypted using the initial position. Second character will be encrypted after the first rotation. Third character will be encrypted after the second rotation. So what happens now? In the initial position, the first character is B. So it will be encrypted to capital B. Fine. Now the second character is E. So second character will be encrypted with this first rotation. So here E is encrypted to C. So the second character is C. Now the third character will be encrypted after the second rotation. What is the third character? E is the third character. So E will be encrypted to A. E will be encrypted to A. So the third character will be encrypted to A after the second rotation. So you will have BCA if the rotor is rotating. So this is how the text will be encrypted using the rotor cipher. Now here we can say the rotor cipher is resistant to brute force attack as well as the statistical attack. Now another cipher for the polyalphabetic substitution cipher is using the Enigma machine. So this is a machine which was originally invented by Scherbius, and this Enigma machine is a cipher device developed and used in the early to mid 20th century to protect the commercial, diplomatic and military communication, and it was actually employed extensively by Nazi Germany during World War II, and this was invented by a German engineer, Arthur Scherbius. And this Enigma has an electromechanical rotor mechanism. So this is the diagram representing the Enigma machine, and this rotor mechanism will scramble all the 26 letters of the alphabet. So this is the keyboard which will have all the 26 characters, and this is the lamp board which gives different kinds of rotations after the keyboard is plugged with this particular lamp board. And we can go for different rotations also. Slow rotate, middle rotor, fast rotor, etc. can be used for rotating the Enigma machine. So this is the Enigma machine, and we have the keyboard here, and we have the plug board which can be changed again and again for giving random rotations. And this is the lamp board, and these are the rotors. Slow, medium and fast rotors are also available. This is another representation of the Enigma machine. You can refer this particular site for further reading, okay, about the Enigma machine. Anyhow, I have given what are the different components that are available in the machine, and what is the code book that is used for the Enigma machine during World War II is also given here. And what is the procedure for encrypting a message using the Enigma machine, and what is the procedure for decrypting the message using the Enigma machine. So this particular part is taken from the Cryptography and Network Security textbook by Farauzen. So you can go through these points to understand how the Enigma machine will be used for encrypting and decrypting, right? So the one part that you have to understand in the Enigma machine, it will have a keyboard, plug board, lamp board and rotors. Using all these four, we can make random settings for the encryption process, which will be agreed between the sender and receiver. And these are the different components. It will have a keyboard, it will have a lamp board, it will have a plug board, and it will have 3 rotors and the reflector which will be stationary and pre-wired. So using these components, it will be used for encryption and decryption process. And the Enigma machine will have a code book which was published that gives several settings for each day. So what is the keyboard and plug board setting used, that will be specified in the Enigma machine. And the procedure for encrypting and decrypting the message will also is also shown here. Please go through and you can understand how it is used for encrypting and decrypting. And the cryptanalysis part of the Enigma machine, obviously it is very difficult. If the machine is got by the attacker, obviously the cryptanalysis can be done by the attacker. So with that, we are completing the polyalphabetic cipher of the substitution cipher. Thank you.